Hello, this is a video about the contact of rough surfaces and also a little bit about plastic deformation in the contact of two surfaces. Please watch the contact mechanics videos before watching this one. I think that's a good introduction before entering into this a little bit more detailed subject. My name is Roland Larsson. I'm from Luleå University of Technology in Sweden. The content of the video is like this. So it's about multi-asperity contacts that are occurring then when a rough surface is coming into contact with another surface. And we'll also discuss what is happening when plastic deformation occurs, which it will at the highest asperities, for example. Okay. This is a nice illustration of a rough surface coming into contact with in this case, a nominally flat surface. So you can see here that when you do that, the nominal size of the contact is B multiplied by A. So that's what you normally call the nominal area, the nominal contact area. While the real area of contact is only in those spots here where the surface actually touches the other surface. So it's only a small tiny spots here. So the real area of contact is always much smaller than the nominal contact area. That is something to remember. And actually you can show that the real area of contact is pretty much proportional to the load. That's not the case, by the way, if you put a surface, a kind of non-conformal surface in contact, like a ball in contact with a plane, then the contact spot area is not proportional. It's not linearly proportional to the load, like in a multi-asperity contact. We have some examples here from a nice work from Almqvist and Perez Rafols, and showing not only multi-asperity contact but also an elastic plastic contact of a surface. So we start here with a surface. Here you have no contact yet. Here's a rough surface down here, and here's the upper surface, the flat upper surface here. So this diagram actually shows the permeability of that means how easy it is to flow a fluid through the gap here in between these two surfaces. The fluid is hindered by the asperities, of course, and so it must flow through the valleys and find its way through the roughness. And the higher the load is, the W is the load, and in this case it's the kind of non-dimensional load. If you increase the load, the surface comes more and more into contact. So if you increase the load to 0.1 in this case, non-dimensional numbers, you end up with this case. Then you have contact spots like this. It's isolated contact patches. And you actually deform the short wavelengths, and of course you decrease the permeability significantly when you put the surfaces in contact like this. So now it's much more difficult for the fluid to pass through the roughness here. And if you keep on increasing the load, you can see that the contact patches are growing, and they continue to grow, and also in this case the maximum load case. Now you have also some plastic deformation here. Then when you release the load, you decrease the load. What is happening then? Well, when you start unloading the surface, now you maintain the contact area pretty much, because the elastic deformation of the long wavelengths are kept, and so it's only the shorter ones that are released. So there is still a very low permeability of this surface. It's very difficult for the fluid to pass through here, through around the contact patches and in the valleys. So of that reason, the permeability doesn't increase as much as if it had been on its way down during the loading process here. And you can see here that you keep on keeping a relatively low permeability until you come to a certain. Now you're back to zero load again, and you can see here that the original surface is significantly smoother than it was before loading the surface, and that's because of the plastic deformation of the asperities. So this example shows a typical behavior of a rough surface coming into contact with another surface and becoming first elastically deformed and then also plastically deformed, and then when you release the load you have the permanent plastic deformation is there, so you have actually smoothened the surface by doing that. So I just wanted to show that as an example. Let's continue to discuss multi-asperity contacts. In this figure or illustration you see two cases. First, the initial condition case with, in this case, 5 contact spots, and in the right hand side here you have increased the load and you have got a few more contact spots like this, and the original ones have grown a little bit. So the thing is, what is happening when the contact load is increasing is that each contact spot grows and more spots occurs, but the average size, or the mean size of each contact remains fairly constant. It's only that additional contact spots come into additional asperities come into contact. And since there is a linear relationship between load and real area of contact for a multi-asperity contact, then you can discuss in terms of friction too. So the mathematics down here is illustrating that. So the friction force is the real area of contact multiplied by the shear strength of each contact spot. And since we know that the real area of contact is linearly proportional to the load, that means that it's a constant multiplied by the normal load multiplied by the shear strength of the contact. And then you can see that you can put the constant multiplied by the shear strength as the mu actually. So mu is constant by multiplied by shear strength. So this shows that as long as there is a linear relationship, the constant here, and as long as there is a constant shear strength of each interface, so each contact spot here, then the friction coefficient will be constant too. So that is the case, and that was discovered by already Leonardo da Vinci, wasn't it? So that explains why the friction coefficient in many cases is independent of the load, as it is here. A little bit more about plastic deformation of the surfaces. Assume that we have a smooth ball or a cylinder and place it in contact with a plane. Then we can see that the plastic deformation starts below the surface. Remember from the contact mechanics videos that the highest stress occurs a small distance down into the material when you have perfectly smooth surfaces. So for metals, and this happens at approximately a mean pressure of 1.2 to 1.4 times the material's yield strength. So then this, if you increase the load more and more, pretty much more, the plastic deformation zone reaches eventually the surface, and you get a permanent deformation of the surface. And that happens at a mean contact pressure of approximately 3 times the yield strength. And if you then continue to increase the load, nothing really happens. The contact pressure can't increase much more. It just increases the plastic deformation zone, and you have a plastic flow of the material. So it remains constant, and that's something we are using for hardness testing. Remember that all these numbers are pretty approximative, but still it's something to remember here that the hardness is actually 3 times the yield strength. That's something to keep in mind. Okay, hardness testing then. So as I said, it's this thinking is the basis for hardness testing. So Vickers hardness, which is a very common type of hardness measurement, is placing means that you place a kind of pyramidic indenter, a very hard surface. You apply a load of 300 newtons on that one, and you create a permanent dent that looks like a pyramid like this. You measure the size of the dent, the area, and since we know that we had a constant pressure in the contact area because it was plastically deformed due to the sharp corners of the indenter, we can compute the hardness as the load, the 300 newtons, divided by the size of the permanent dent here. So, and that's the definition of hardness. So we talk about Vickers hardness in kilopounds per square meters, and so 400 HV is 400 kilopounds per square meter. So that's something like 3,900 megapascals. So you can define it in megapascals as well. This knowledge about knowing that the pressure is, the contact pressure is limited to the hardness of the surface is very useful. So in tribology, we normally say that the contact pressure can't be higher than the hardness number, the H number here. So even if that's not perfectly true, it's a very good approximation, and we can use that to approximate the real area of contact of a rough surface in contact with another surface. And we can, the reasoning behind that is that we assume that we have the surface with pretty sharp asperities, so relatively high slope. So at reasonable loads, you get so high contact pressures that you reach the hardness level and you get a plastic deformation of it. So it's more or less all the contact spots you have reached the plastic deformation limit. And you can assume that you have it in all the spots, and then you can then you know that the contact pressure everywhere is H. It's the same everywhere. It's the hardness, and remember now that it's the hardness of the softer material. If you have two materials with different hardness, it's the softer one that is plastically deformed first, of course. So that means that you can compute the real area of contact by simply assuming that the normal load is the real area of contact multiplied by the H, or the real area of contact is the normal load divided by the hardness. So you can play around with this now by checking this exercise. You can stop the video and you can solve this problem. Okay, I hope you have done that now, and then we can do the math here. So assume now that we take this the flat punch with the size of 2 by 2 centimeters. You press it into the contact with a flat smooth surface. You apply the load of 40 newtons only. The nominal contact area is then 20 by 20 millimeters. That means 400 square millimeters. Now, then we can also compute the nominal contact pressure, which is simply 40 newtons divided by 400 square millimeters. That is 0.1 newtons per square millimeter, and that is 0.1 megapascal. So it's very low nominal contact pressure. Okay, now assume that we have a kind of normal roughness of the surface with relatively sharp asperities that makes this approximation valid, that the real area of contact is simply the load divided by the hardness. And we can assume that the hardness is around 1 gigapascal in this case. So then it's easy to compute that the real contact area is the load 40 divided by the hardness, which is 1 gigapascal, or 10 to the power 9 pascals. So the area will be something like 0.04 square millimeters. So this is the real area of contact. So the ratio between the nominal and the real contact area is something like 10,000. So 10,000 times smaller real contact area than the nominal contact area. It's only the two surfaces, they only touch each other in tiny spots of 0.04 square millimeters. That is something like 0.2 by 0.2 millimeters. So it's very much smaller than the nominal area of the 2 by 2 centimeter punch here. So that's something to think about when we talk about tribology. There is a very much smaller real area of contact than the nominal area. In this case, the load was relatively low, of course, but still, if you increase the load, say 100 times, you still only have a ratio between the nominal and the real area of contact that is around 100 then. So, is this true then? Is it useful to use that law? Well, here you can see some example where we have been doing a more exact computing of the contact area, and using we can use contact mechanics theory to solve the linear elastic contact of a rough surface. So here you see that by increasing the load, the blue spots represent the contact spots. So increasing load means that more and more of the surface come into contact with the other surface. Assuming that this idea about perfect plasticity, then using that the load, the real area contact is force divided by h, you get something like this. So it's not exactly the same, but it's a good representation, I would say. So it's for most purposes, this approximation is useful for engineers. And finally, I want to show some computer simulations. It's a little bit older ones, but showing a rough surface sliding in contact with another rough surface. It's not the nicest simulation maybe, but it shows something that is very important to remember, that surfaces, first of all, they only touch in a few tiny spots, and in those tiny spots the pressure becomes very high. So normally you reach some plastic deformation levels there. So even if you have two very shiny smooth surfaces, even if you have that and you put them in contact, they still only touch in a few spots. That's something to remember when you work with tribology. And the consequences are, of course, that you deform the highest asperities pretty soon. You run them in, and we will discuss that in later videos. So that's all for now. Thank you very much.